Hello and welcome to Database Management Systems. I'm Javita Christie, and in this video I'm going to explain a little bit more about functional dependencies in relational database design. So we are going to study how to calculate a canonical cover, and in order to do that we are going to study some rules called Armstrong's axioms, and we're going to do some mathematical proof related to that, related to those rules. So let's start. So first of all, what are Armstrong's axioms? Armstrong's axioms, and first we'll see what axioms are. So axioms are rules of inference. They provide a simpler technique for reasoning about functional dependencies. So these rules allow you to evaluate and sometimes even reduce the number of functional dependencies, and that is why we are basically doing all these rules. So it is used to find logically implied functional dependencies. So sometimes when you're given a set of functional dependencies, using that set you can find out other functional dependencies, and so you can remove some of the dependencies which are already given to you. Because as I mentioned in my previous two videos about the same topic, functional dependencies, if they are non-trivial, then they are not good, because the more functional dependencies you have, the more redundancy you'll have. So in a DBMS, a database management system, we try to avoid the number of functional dependencies that are present in any given situation. So that's why we use all these rules, and these rules would help us to reduce the number of functional dependencies. Now let's see what are the three Armstrong's axioms. And these are the three basic rules which are available. So let's see the first one. It is known as reflexivity, and it's very easy to understand. It simply says that if A is a set of attributes and B is a subset of A, or B is equal to A, then A determines B holds. And this is very easy to understand. If you look at it even logically, this is a type of a trivial functional dependency where the right side is actually a subset of the left side, and if the right side is equal to left side, then obviously it's like saying A determines A, which is always true. Then you have augmentation rule. Augmentation rule is if A determines B holds, that means A determines B is true, and C is a set of attributes, then you can augment C on both the sides. That means you can write down CA determines CB. But remember that C should be same. That means C can be one attribute or C can be multiple attributes, but they have to be the same. They have to match on both the sides. So you can augment attributes in this manner. Then you have transitivity rule, and this is a very popular rule even in mathematics. So most of the people already know this. It is A determines B. If A determines B and B determines C, then A determines C. So we are simply taking this value with this value. So we get A determines C. Now these are the three fundamental rules of Armstrong. And other than these, in order to make our calculations simpler, there are other additional or secondary rules available, which can be proved using these three fundamental rules. And there are actually 5 additional rules available, but I'm only going to consider 3 in this video, and I'm going to prove only those 3 because the other 2 are very simple, and it does not require that you remember those or that I mention those. So the additional Armstrong's axioms are: number 1, the union rule, which says if A determines B holds and A determines C holds, then A determines B, C holds. So what what exactly you did is, if A determines B is true and A determines C is true, and you can see that the left side is matching for both, then you can combine the right side. So it becomes A determines B, C. The next rule is the decomposition rule, where A determines B, C. It's the opposite of the union rule. So if A determines B, C is given to you, you can decompose it into A determines B and A determines C. And this is a very important rule which we will be using very frequently in this video. And the last rule is a pseudotransitivity rule, which says that A determines B if this is true, and CB determines D is true, then AC determines D. So what you actually did is, in this equation, that is CB determines D, you replaced B with A and got AC determines D. So this is pseudotransitivity, and this is also correct. And we're going to prove these rules one by one using the fundamental rules, because like I said, these are additional rules and they can all be proved by using the fundamental rules which we saw earlier, which are reflexivity, augmentation, and transitivity. So let's go ahead and prove the union rule. The union rule is A determines B is true and A determines C is true. Then A determines B, C must be true. And we are going to prove this using these three rules given right here. So you have reflexivity, augmentation, and transitivity. And you can only use these three. You cannot use anything else other than these three. So using these three, we are going to prove this particular equation. So first of all, since on the right hand side, for the place where I actually have to prove, which is right here, on the right hand side I require BC. So I'm going to try to bring that, and in order to do that you have to follow a step-by-step process. So in my step 1, I'm going to write down A determines B, and in bracket you should mention that this is given. This is given because you are told that A determines B is true and A determines C is also true. So you can use that as you like. Now in this, I want to make sure that I get what I want. So what I'm going to do for this part is I'm going to add, in this section, I'm going to add A. I'm going to augment A. So basically what I'm doing is, in my next step, I will write down double A equal to AB. So what I simply did is augmented. This is using my augmentation rule. So I'm just going to write down over here AUG for augmentation. So using augmentation, I have done double A determines AB. Now the next step is, I'm going to take the second one, that is A determines C, which is given to me. So this is given. A determines C is given. Now using this, I'm again going to augment something in this, and what I'm going to augment is B, because right here I have a B. I have right here I have AB together, so I want AB in this position also. So I'm going to write down as my fourth step, AB determines BC. So I've augmented B into that. So again, this is my augmentation rule. And once I'm done, now you can see that using this equation in step 2 and equation in step 4, I can apply a transitivity rule, because A determines AB and AB determines BC. So I can apply AA determines BC using transitivity. So in my fifth step, I will write down AA determines BC and I reached here using transitivity. Okay, and transitivity applied on step 2 and step 4. This gives me this particular equation right here. And this can be simplified. You can write this as A determines BC because you do not require the same attribute twice on one side. So that's why you can write it as A determines BC, and hence you can say that this is proved according to the union rule. So this is how you can give a proof for the union rule. Now let's go ahead and see the next one. The next one is the decomposition rule that says A determines BC. It is true. Then A determines B holds and A determines C holds. So we have to prove two things from only one thing that is given to us. So I'm going to go ahead and prove this thing now. So in order to be able to prove this decomposition rule, I'm going to do something very simple. And that is, I'm simply going to write down this is my the first thing that I'm going to write down is just repeat whatever is given. So A determines B, C is given to me and I'm just repeating it. Now in the second step, I'm going to write down something which is quite common. That is, I'm going to write down BC determines B. Now where did this rule come from, you'll ask me, because it's not there given. So this is nothing but plain old reflexivity. And can you see that from reflexivity it says if A is a set of attributes and B is subset equal to A, then A determines B holds. So right here B is a set of attributes, or B is just an attribute, and I've simply written that this is a trivial dependency because I'm writing BC determines B and B is a subset of BC. So this can be written directly, and now you can see that my work is very easy. I simply have to write down A determines B, because if you combine these two you can see reflexivity. Here also there is BC, and here also there is BC, and here also there is BC. So this is transitivity. I'm writing it, okay, I'm writing it fully. So transitivity of rules 1 and 2. This is transitivity. Now in my next step, I'm going to write down the same thing for A determines C. So you can guess how that can be done. So you can simply write down now, in order to prove C, that BC determines C. Again, this is the reflexivity rule. I'm not writing it completely. And now using transitivity between, you will take 1 and 4. If you take transitivity, then this BC is common with this BC, and so you can get A determines C. So this is my transitivity rule between steps 1 and step 5. So this is what I get, and hence you can see that using this rule right here, using the step 3 right here, I have proved A determines B, and using step 5 I have proved A determines C. So both the things have been proved, and this is my decomposition rule. Now let's go ahead and see the next one. So we are going to try to prove pseudotransitivity, and this is very simple to prove because it comes from transitivity and you don't really need to do much in order to prove this. So first of all, what is given to you is A determines B, and then what's given to you is CB determines D, and what you need to prove is AC determines D using these rules given right here. So let's see how this can be done. I'm going to begin by once again writing down what is given to me, that is A determines B, and you can write down over there that this is given. And you can also mention the second rule directly, which is already given to you, the second statement. I'm not using it right away, but you can write it, there is no problem. So these two things are given. Now, in my third step, I'm going to do a simple augmentation. Here I have BC or CB, so I just want BC or CB here also. So I'm going to augment over there C. So it gives me AC determines BC. So this is a simple augmentation. And now using this, I can do a transitivity, which is quite clear. If you check 2 and 3, then here you have CB and here you have CB or BC. The order doesn't matter. So using that, you can say that AC determines D. So number 4 is simply AC determines D, and this is by applying the transitivity rule on 2 and 3. So this is what I get, and you can see that I have proved what I was supposed to prove right here. So this is how I can prove all the rules given to me directly. I don't have to do much in order to prove all these rules. So that's why they are called additional rules. Now let's see what a canonical cover is. This is the application of the rules that you just learned. You know that you learned the rules which are Armstrong's axioms. These rules can be applied to find a canonical cover or irreducible set. So let's see what that is first. It is a simplified, reduced version of the given set of functional dependencies. So if you are given a set of 10 functional dependencies and you realize that some of those are not required because they can be deduced from the ones that are already given to you. So that's why you remove some of the dependencies and form a set from which you can no longer reduce anything. That is called a canonical cover or an irreducible set of dependencies. It's the same thing. So we are going to calculate this using the Armstrong's axioms that we. So in this part of the video, I'm going to explain how to calculate a canonical cover or an irreducible set from a given set of functional dependencies using the things that you have studied before, using the Armstrong's axioms. So these are the dependencies given, and your table contains 3 columns A, B, and C. The dependencies are A determines BC, B determines C, A determines B, and AB determines C. So we're just going to try to reduce them one by one. And in order to be able to do that, the first step is to decompose whatever you can. So whatever you can decompose, that you are going to try to decompose first, and then you will do the rest of the things. So you can see here I have A determines BC. So I'm going to decompose that and write down A determines B and A determines C. Now if you look at it carefully, you can see that A determines B is present here also and here also. So I don't need it 2 times. I can remove it once. So I'm going to remove one of those. So I can remove this A determines B part. And now I'm going to rewrite what I have. So I have A determines C. Then I have B determines C. I have A determines B, and I have AB determines C. So we have 4 dependencies. Now if you look at all of these carefully, you will notice that these are applying the transitivity rule. And you can notice that very clearly because A determines right here, A determines B, and then B determines C, and therefore A determines C. So actually, if you are given these two rules, then you can always derive A determines C from there. So you don't require A determines C, which is given to you here. So we are going to remove this. And now it's always good to rewrite what you have. So I'm going to rewrite all the rules that I have now. And those rules are B determines C, A determines B, and AB determines C. So these are the 3 left. Now again, I can do some calculations here too. So I'm going to show you those calculations down below as a rough work. So you have B determines C. We are going to use that B determines C in order to create AB determines AC. And the reason why we are doing that is because we can perform augmentation. So I'm going to make this AB determines AC. So I have done nothing but augmentation. So this is AB determines AC. And now I've got a second rule that is A determines B. So I can make this side also AC, which means what I'm necessarily going to do is augment C into this. So that would give me AC determines BC. So this is another augmentation. And now you can see what I have is AB determines AC and AC determines BC. So this leads me to something called transitivity. So using these two rules, I have again transitivity, and because of that, I can generate, in this case, AB determines BC. And then obviously I can decompose this to be AB determines C. So this is a decomposition. I'm not going to write the full thing. Okay, so this is a decomposition. So you can see that I am able to get this. And this is exactly equal to this rule given right here. AB determines C. You can see that I'm getting that using this also. So I don't actually need this rule. This can be removed. So what I am left with is B determines C and A determines B. So this is my canonical cover. Using these two, I can derive all the other rules that are given here. So only these two are needed. Others can be derived using these two. So this is called a canonical cover or an irreducible set. And once again, just to give you the final answer, it is this. The canonical cover is A determines B and B determines C. So this is how you can find canonical cover using Armstrong's axioms, but it's not always easy to spot this in a given set of FTs. How do you know that which rule to apply? You won't always know this, and it is difficult to understand whether to apply a rule or not. So that's why there is a shortcut in order to perform these calculations. That is using extraneous attributes. So the concept of extraneous attributes deals with removing extra attributes that do not add any value to your current functional dependency, to your current set of functional dependencies. So such attributes are removed one by one. And first I'm going to give you a formal definition of extraneous attributes. Afterwards, I'll explain the same thing using an example, and at that time you'll understand it. I'm sure you won't understand what I'm showing you right now, but it's important to remember these rules in case you need to write it down somewhere. So, what is an extraneous attribute? An attribute of a functional dependency is said to be extraneous if we can remove it without changing the closure of the set of functional dependencies. So basically what this statement says is that extraneous attributes are just extra and they are redundant, and if you remove such attributes from a functional dependency, it does not change anything. So such attributes can be removed. Now there are rules in order to remove such attributes, and those are right here. You may not get this right now, but you will get this when I explain with an example. So the first rule that you see right here applies to the left side, and the second rule applies to the right side. And I'm not going to explain these rules in detail here because I'm going to show an example. So you can go ahead and memorize those or try to understand. You can come back to this part of the video once you understand the example, and I'm sure you'll get those rules then. So let's quickly go and do the example, which is a shortcut method to find canonical cover or irreducible. So this is the relation given, relation R. It contains W, X, Y, Z, 4 attributes. And the dependencies, functional dependencies, are X determines W, WZ determines XY, Y determines WXZ. And what you need to do is find the canonical cover. So first of all, we are going to rewrite these by performing decomposition. So decomposition is your first step, and a step that you must never forget. So step 1 is decomposition. I'm sorry for my bad handwriting. I hope you understand that I have written decomposition. So decomposition, and what you need now is decompose whatever is not decomposed. And remember, decomposition can be applied only to the right side. So in this case, I have X, Y, and W, X, Z. So here I have more than one attribute. So only to that part I can apply decomposition. So the first dependency remains as it is. X determines W. The second one can become WZ determines X. Then WZ determines Y. Then you have Y determines W. Y determines X. And Y determines Z. And now what we will do is try to reduce this list. We have a long list and we have to reduce this to the minimum number of dependencies required. So we are going to begin with the right hand side of the arrow. That is your second step, working with the right hand side of the arrow. So your second step simply involves the right side. So what you're going to do with this right side is you're going to check each and every dependency. So for example, you are checking X determines W. Now try to find out closure of X. What would be the closure of X when you are keeping X determines W within your list? So I can list out closure of X will be X itself, and because X determines W is present, it will be W. Then can I add this? No, WZ is not present, Y is not present, so that's it. This is the closure. Now let's see what is the closure of X without this dependency. So what I'm basically doing is, just for an example, I'm going to remove this. So this dependency is no longer available to you, and now using the rest of the dependencies, can you still get x comma w as the closure? And the answer to that is obviously no, you cannot get it, because all you will get at this point is x. So you will get x, but then using x you cannot get w because this dependency is gone. So this is simply giving you x. So you can see that these two are not matching. So when they do not match, then you can say that this dependency which is given is important right here. And the reason why it is important, because if you remove it, then the closure is changing. So if the closure changes, you cannot remove that dependency. So this is my first dependency, which I am actually going to keep. So I will remove this cross mark that I put in front of it, and I will put a tick mark over there so that we can remember later on that this is the one we are keeping. Now let's see wz determines x. That is the second dependency. So number 2 is wz determines x. What would you do now? So in this case, again, we are going to apply the same rule, that is wz plus. If we keep this dependency, we are going to get wz x. So we will get wz x. We will also get y. And I'm going very quickly in this. If you don't know how to calculate closure, you can watch the previous video. I have linked it down below. So wz x y, and then using y w. So I actually got all the attributes. I don't have to do anything. So this is almost like a, not almost, it is a candidate key. Now let us see what happens if I remove wz determines x. So what I am talking about is removing this dependency. So now I am no longer considering this, and I'll try to find out the closure of wz. So wz plus is equal to, I can obviously add w and z. Now using w and z, can I add y? Yes, I can add y. All that is remaining is x, and I can add x also using this. So x is also added, and so you can say that the closure remains same. So these two are actually the same, and that's why this dependency right here, which you see, is not required. You don't need this dependency at all, and it can be removed. So I've already done a cross mark here. So we'll keep the cross mark. I don't have to change the cross mark. Okay, now let's move on to the next dependency, that is wz determines y. So for wz determines y, we again need to find out wz plus, and in this case we are going to keep this dependency first. We are going to consider wz determines y to be present, and just to avoid confusion, we have removed this dependency, so it is no longer available. Now using the rest of the dependencies, we need to find out if wz plus remains the same or not. So obviously right now, because this dependency is available, wz plus will be equal to w comma z comma y, these three attributes, and what is missing is x. Can I get x? Yes, I can get x using this dependency right here. So I am getting x also. Now this is using wz determines y. Now suppose this is gone. So let me put a cross mark. If it's required, I'll remove it afterwards. So this is gone. Now without it, can you get the same result? So now again I'm going to calculate wz plus, and obviously I can get w and z, but I don't have this dependency anymore, so I cannot directly put y. So can I get y any other way? No, you will notice that you cannot get y in any other way. And remember, this dependency, which is right here, the second one, we have already removed, so we cannot use that either anymore. So you can see that this is the closure now. There are two attributes missing. So that's why this particular dependency right here is important. You cannot remove it. And hence I will go ahead and remove the cross mark and convert it into a tick mark. The next dependency we have is y determines w. And this might look like a long process, but it's long only because I'm explaining it to you. When you try to do it on your own, you'll be much faster because it's a lot faster to do when you do it on your own. So the fourth one is y determines w. So I'm going to try to find out y plus. That of course gives me y and w because I'm considering this dependency also. So y and w, and what else does it give me? It gives me x, it gives me z. You can check it out for yourself. So I got all the attributes. Now imagine that this dependency right here is not present. So without that dependency, can I get the same results? So y plus now is equal to y, of course. Other than y, what can I get? I can get x, I can get z. Can I get w? Yes, I can get w because it's present here. So because of x, I can get w also, which means this thing did not change. There was no change, and that's why I can remove this dependency. It is not required. Without it also, I can get the same result. So you can remove this dependency from here, and I have already applied a cross mark here. I'm going to leave it as it is. Now the next dependency is y determines x, and before we move there, let me just cross this out so we know that this is removed. So this is removed, and now let's see y determines x. So in my next step, I'm calculating y determines x. So first I'm going to do y plus using y determines x. So that's why I'm keeping y and x both at the same time. Now because I have x, of course I can add this part. So I can add w. What is remaining? Z. Because I have y, using this dependency right here, I can add z also. So I'm going to go ahead and add z to this. So I got all the attributes once again. Now let us try to remove this dependency which is given here. So this dependency we are trying to get out. Now when it is out, do I get the same result of y plus? So I'm calculating y plus, and what that gives me now is y, obviously. Now using y, what all things can I achieve right here? So using y, I can get z, but I cannot get anything else right now. So using y, I can get z, so I'm going to write down z using the last dependency. Using z, can I add anything to this? No, I cannot. So you can say that this set is over right here. So two attributes are missing, and that's why this dependency right here cannot be removed. So this dependency we have to keep. So I will remove the cross mark next to it right here, and I will put a tick mark because this is the one that we are going to keep. And now for the last dependency, which is y determines z. So this is my sixth one. Y determines Z. So once again I calculate Y plus. And what do I have in Y plus? In Y plus, because I'm considering Y determines Z, I have Y and I have Z. And because of the second last dependency, I have X also. So what is remaining? I have X, Y, and Z. I don't have W. Can I get W? Yes. Because of the first dependency, that is X determines W, I can have W also. So I have all the attributes. Now let me calculate Y plus without using this dependency right here. So I'm going to go ahead and put a cross mark here just for this example. So now without it, can I get the same result? So Y plus now will obviously contain Y. Using that I can put X also because of the second last dependency. Using X I can get W. But using W now, can I get Z? So Z, you know, it's not possible. And that's why this thing right here is changing. So these two values right here are not matching. And that's why Y determines Z is a necessary functional dependency and I cannot remove it. So what we're going to do is simply take this off and put a tick mark right there. So the dependencies that I have left are X determines Y, WZ determines Y, sorry, X determines W, WZ determines Y, Y determines X, and Y determines Z. These are the four dependencies left out for me. So now at this point, I've filled this page completely with all the scribbling that I've done, so I would definitely have to move to the next page in order to continue. So I'd like to point out that there are four dependencies left, but this is not the end of the example. You still have to consider these four dependencies and talk about their left side. So we are done with the right side, but we have to talk about the left side now. So that's what we are going to do now in the next. So from the previous example or from the previous calculation, whatever values were left, whatever dependencies were left, I'm going to write them down. They are X determines W. Then we have WZ determines Y. Sorry, this is W. And then we have Y determines X. And we have Y determines Z. So now from these, there is only one dependency that is having two attributes on the left side. So whatever dependencies are remaining which do not have more than one attribute on the left side, those dependencies you don't have to consider because you cannot reduce them anymore. But the dependencies that have more than one attribute on the left side, those you can work on. So what you need to do for this is calculate WZ plus. Let's calculate WZ plus. What do you get? If you calculate WZ plus, you'll obviously get W and Z. And then because of W and Z, sorry, I think yes, this is supposed to be not WZ determines Z. This is WZ determines X. So right here it is X. Okay. So now I can move ahead with my calculation. I have W and Z. I can get X. And using X, I can get W. Now can I get Y using W and Z and X at the same time? So I'm not able to get Y using that. So this is my closure. Now let me check for WZ. So I'm going to calculate now W plus. Using W plus, what can I get? I can get W. Can I get any other attributes? No. If I calculate z plus, what can I get? I can get only z. I cannot get any other attributes. So you can see that these two things right here, they do not match wzx, which is given by wz plus alone. So that's why this dependency right here, this is an important one. We cannot remove it, because if you remove it, you are not able to get the same type of closure again. So whatever list you have right now present here, these four functional dependencies, this is your canonical cover of our original question, and our original question contained these dependencies. And don't think that we've increased the number, because actually this is two dependencies and these are actually three dependencies because of the number of values. So we've actually reduced the number, and this is your final answer for this. So this is the video where I'm going to end all the calculation video in this series of lectures. Thank you for watching. See you in the next video.